For topic 6, we're going to look at applications of systems of linear equations, okay? We do need to revisit a definition that we haven't seen since 6.2 or 6.3, okay? And that is direct translation, okay? So remember that direct translation is the process of converting words to math. And this is a pivotal part of solving word problems in an algebra class or in a section of a class involving algebra, okay? We have to take the phrases, the sentences, the paragraph, and we have to pull out the important information and then create expressions or equations out of that, okay? And part of that process is to assign a variable to the unknown. So that's our goal, assign a variable to the unknown. Now, back in chapter 6, we had a situation where we may have had more than one unknown, but we could always write all of the unknowns in terms of one. Okay, so you would assign the variable to what you knew the least about, and then you could still come up with expressions for all of the others in terms of the first. Okay, in some situations, however, you're going to need more than one variable, and that's exactly what's going to happen here. Not only are we going to need more than one variable, we're going to need more than one equation. Okay. So let's look at a pretty straightforward, simple example, and then we'll look at one that kind of has more going on, okay? So example 6 says, write the system described below. So number 1, we want to see your system, and then solve and write the answer as an ordered pair. 2, we want to see you solve it, so we want to see some kind of algebraic method to show how you solve this, and then we want you to write your answers in ordered pair. Sometimes with word problems involving systems of equations, you wouldn't necessarily write your answer as an ordered pair because the application part of it wouldn't make sense. But in this first one, we can write our answer as an ordered pair. Okay, so we know we're going to be solving a system because it says write the system described below. We're going to solve it and we're going to write our answer as an ordered pair. Big hints that you're dealing with a system of equations, meaning we're going to need two equations, two variables. All right, so first we have the sum of two numbers is 62. Okay, next we have one number is 12 more than the other. Find the two numbers. Okay. Well, we have two very distinct situations. We know that the two numbers have a sum of 62. That can be one equation all on its own. And then the second piece of information that we have is that one number is 12 more than the other. So we need to write an equation for that. Okay, so two equations, two variables, two unknowns. So it does not matter what variables you use here, but let's say that we let x equal the first number and let y equal the second number. Okay. Now we have this first sentence that says the sum of two numbers is 62. So that would just be x plus y is 62. That's your first equation. Now the second equation, we have to do some more work. It says one number is 12 more than the other. It doesn't specify which number is 12 more than the next, so you kind of pick one. So we're going to say x is 12 more than the other number. So x is the other number plus 12 more. And now we have a system of equations. Okay, so this right here is our system. Do keep in mind it's two equations, two variables. And then when we write the two equations, we just put this curly brace beside them. That tells the reader, hey, these two things go together. We're solving them together. This is a system. Okay. Now, as far as how you solve this, you can solve using addition or elimination. It does not matter. I will tell you this one is kind of made to where substitution is going to be a little bit easier. Okay, so we already have the second equation, solve for y. Or no, solve for x. Ooh, that was scary. We have the second equation, solve for x. So we're going to take this value for x, plug it into the opposite equation for x. Okay. So we have x plus y, but x is y plus 12. And then the rest of the equation is plus y equals 62. So we now have an equation in a single variable that we can certainly solve. We want to start by combining like terms on the left. So I have y plus 12 plus y. So I can combine my y's. That would be 2y plus 12 is 62. I want to get my term containing the y alone. Okay, so that means I need to move the 12. I do this with subtraction. On the left, 12 minus 12 is 0, leaving me with just 2y. And then on the right, 62 minus 12 is 50. Well, I need to get my y alone, so I need to undo the multiplication of 2 and y. So I would divide both sides by 2. 2 divided by 2 is 1. 1 times y is y. And then 50 divided by 2 is 25. So we're told that we need to write our answer as an ordered pair. So over here on the right, I'm going to start my ordered pair. I don't know what X is, but I do know that Y has to be 25. Okay. Now, how do I figure out what X is? Well, I can take this value, let's use a different color here. I can take this value for Y and plug it into either of the original equations. So let's say we plug it into that second equation for Y. Okay. So that gives me X equals Y, which is 25, plus 12. And 25 plus 12, that's all I have to do to figure out what X is. That would be 37. Now, just to be totally good, let's double check this, okay? We know the two numbers that we have to add up to 62. So let's go ahead and make sure that X plus Y really is 62. So X is 37, Y is 25. We want to make sure that adds up to be 62. I like to do my addition vertically. It just makes more sense in my head. So 25 and 37. Well, let's see. 5 and 7 is 12. So I keep a 2. I carry a 1. 1 plus 3 plus 2 is 5 plus 1 is 6. So we do get that 62 equals 62. Everything checks out. We can say with confidence that the two numbers are 25 and 37. Okay. Now, ordinarily with a word problem, I would say something in words like the two numbers are 25 and 37. But this problem specifically said, hey, write your answer as an ordered pair. So we did. All right. So that is a system of equations mixed in with a word problem. Okay. Not the hardest thing you've ever seen there. Okay. Now, next up for example 7, this is more of a real world application. And this is a very classic example of dealing with systems of equations where you're dealing with cost, revenue, profits, things like that. Okay, so example 7 says a company that manufactures running shoes has a fixed cost of $300,000. So, regardless of the number of pairs of shoes they produce, they're always going to be spending $3,000. That could be rent, that could be utilities, that could be payroll. Okay, that could be whatever. Okay, additionally, it costs $30 to produce each pair of shoes. Okay, they are then sold at $80 per pair. So we got a lot going on here. All right. So part A says write the cost function C of producing X pairs of shoes. This one flat out tells you the variables. Okay. So we want to know what the cost is when we produce an unknown number of shoes. We're just going to call it X. Okay. So we would say, well, C equals now, the cost to produce shoes, we have fixed costs. Remember, that could be rent, utilities, and then payroll, for example. So we know it's going to cost us 300,000 no matter what. And then in addition to that, we need to have additional costs of $30 per pair, and we're letting X equal the number of pairs of shoes. So we have 300,000 plus 30x, and this is our cost function. So fixed fee or fixed cost of 300,000 and then an additional $30 per pair of shoes. Think of that $30 as like materials for the shoes, okay? Now, part B says write a revenue function R from the sale of X pairs of shoes. So the revenue, the money that we bring in, well, we sell each pair of shoes for $80. So R is the revenue, and it's going to equal 80 times X. Okay, again, we're selling X pairs of shoes. We don't know how many pairs of shoes. We're just going to say X, but we know that each pair of shoes sells for $80. Okay? Now, part C says determine the break-even point. What does this mean? Now, back in chapter 6, I think 6.3, we talked about break-even problems, okay? We were dealing with linear equations in one variable. It was kind of a different situation there, but the same thing is showing up here. So break-even problems are really common, and you will see break-even problems a lot when you're dealing with cost and revenue, okay? So the break-even point means when do we have cost equal to revenue. Now, our goal is for our cost to be less than the revenue. Of course, we want to make a profit, but we need to know what our break-even point is so we know what to push. So once we know our break-even point, we know, okay, if we sell this many pairs of shoes, we are not going to make any money, but we're also not going to lose any money. And then we know that if we sell more than that, we'll start earning a profit. If we sell less than that, we're in trouble, okay? So let's figure out what the break-even point is. And remember, it is when cost is equal to revenue. So we want to take our cost function and set it equal to our revenue function. So the cost function is 300,000 plus 30x. The revenue function is 80x. So we have cost equal to revenue. Now, if we can solve this for x, we'll have a point where we would break even. We are not going to make any money, but we're also not going to lose any money. She's mad again. I'm sorry. So we want to get all of our x's in a single term on one side of the equation. So ordinarily, I put my variables on the left, but in a situation like this, I'll save one step by moving them to the right. So I'm going to move my 30x's to the right. Now, when I do that on the left, 30x minus 30x is just 0, and that's going to leave me with 300,000. And then on the right, 80x minus 30x is 50x. Okay? Now, if I can get the x all by itself, that means undo the multiplication of 50 and x, then I'll know how many pairs of shoes I have to sell to completely break even. So I need to divide both sides of the equation by 50. On the right, 50 divided by 50 is 1, leaving me with just an x. And then on the left, we have 300,000 divided by 50. Is that right? 300, 1, 2, 3 divided by 50. We get 6,000. All right, so x equals 6,000 pairs of shoes to break even. All right, so if we sell exactly 6,000 pairs of shoes, we don't make any money, but we don't lose any money. If we sell more than 6,000 pairs of shoes, then we'll start earning a profit. If we sell less than 6,000 pairs of shoes, we're in trouble. We're losing money at that point. Okay, so the break-even point, you've seen it now in two different ways. You've seen it with a system of equations, and we saw it in the previous chapter with just linear equations in one. So there you have it. That is systems of equations in two variables. I think it's super fun. I really enjoy them. There's lots of different application type problems. So just be confident with your direct translation skills because you could have other situations where you're creating these two equations. Kind of think back to not chapter, but example 6 here, how we had to use direct translation, understanding there were two different components that we had to create equations for. All right, but that's it. That's systems of equations. Know how to check solutions, know how to check by graphing, know how to solve using substitution or elimination, and definitely know how to set up a word problem.